we assume first, in the first set, assume a PT1 process. A model given with chapter 9.2, the f of p of a PT1 is simple k divided by 1 plus pt, and this leads to a step response invariant filter function. We need for this is b1 z to the power of minus 1 divided by 1 plus a1 z to the power of minus 1 with, well, you can read it, we have discussed it, developed it without any change. A1 is minus e to the power of minus sampling time divided by time constant, and b1 is k1 plus a1. Okay, this is just given so that we can write our model now with the correct letters. F of z, that is my model, and the input values are the output values are called y of k, and the input value is the process model. Yeah, should be clear with this. What is das? Also, warte mal. Process model. So we need a good identification, otherwise this doesn't work. That is xm, and the input is the controller output y of k. So now we have it, xm of k, and we can now with my equation here I can calculate that the output of the process xm of k, actual time point, is negative a1 times xm one step before, is the recursive part of this algorithm, plus b1 times input y of k one step before, plus b1, and I replace now the b1 here with this k1 plus a1. That is also different to other designs. Here I have a mix of A's and B's and process K's. So we can do this. So we have now in this expression only my a1 as a parameter, not a b1. And my k, the gain of my controller, the process gain k. Okay. In my paper I use indexes. Maybe I should do this here also in my paper. The process model has a gain km and the time constant tm, so I should be consistent in this way. This is the process model km. Okay, times input value one step before, y of k minus 1. This is the model output in the actual time point k, and now the predictions come. K plus 1 is minus a1 xm of sorry, schlechter Tag heute. Sorry, of course, here we have a minus 1, a previous step. Xm of k, that's z to the power of minus 1. Of course, here is a delay in the past. So now we have here xm of k. Sorry for this small mistake. Plus km 1 plus a1 times y of k. Okay, here note y of k is the goal of my calculation. Yeah, y of k I want to have. The controller design uses now these equations finally to define y of k. But I want to look further in the future. If I have k plus 2, you see this is minus a1 xm of k plus 1 plus km 1 plus a1 y of, and now different, I have mentioned it, in my deadbeat design, I have now a new controller output in Richalet design. This output is held constant, is assumed to be constant. Yeah. So this now it can be changed in that way that we can write xm k plus 2 is, and I replace now the xmk plus 1 with this expression. Look what happens. Then we get a minus a1 times parentheses now followed by xmk plus 1. Xmk plus 1 is this expression, is minus a1 xm of k plus km 1 plus a1 y of k, parentheses closed, plus, and now this second part, plus km 1 plus a1 y of k. You see, this leads to a rather large new equation, but we can put together these equations in the following way. Now the trick of Mr. Richalet is astonishing or strange, or what else we can say. Next step is xm of k plus 2 is first minus a1 times minus a1. Note a1 is negative, so these are both positive numbers. So minus a1 times minus a1 is minus a1 squared times xm of k. And then what else? Minus a1 times this a1 times km 1 plus a1, and I extract now the y of k. So I make parentheses, say plus, and I have a minus a1 times km 1 plus a1 y of k plus km 1 plus a1 y of k. So look, km 1 plus a1, the b1 here, this is b1, this is b1, and this is 1 times, and this is multiplied with minus a1. So we can write this is minus a1 squared times xm of k plus y of k times km 1 plus a1 is this part, and I extract km 1 plus a1, so this is a 1 times km 1 plus a1, and this is minus a1 times km 1 plus a1, so this is minus a1. And you see now, copy minus a1 squared times model output at time point xk plus y of k, unchanged. But now you see this is km, and now the advantage of using not b1 but replaced with km 1 plus a1, you see 1 plus a1 times 1 minus a1 can be put together as 1 minus a1 squared. So this is the first result. Or I write in correctly. The a1 is negative. This must be written as 1 minus a1 squared. So this is a writing, because if I do this a third time and a fourth time and many times, if I do this h times, h could be 50 or 100 or any number, k plus h, then this is can be done several times. We get then minus a1 to the power of h times xm of k plus y of k times 1 minus a1 to the power of h times kn. Okay, so far. Stop for looking. So with this last equation, what can we do? We have a controller output y of k, and this y of k can be used to predict the model output h steps into the future with the given model parameter a1 and kn. Starting with the actual model output k. So this is the starting point, this is the ending point, the horizon, and with this y of k I can define this horizon. And now we put this process output value together with, where are the equations, with my lambda, yes, here, with this together, that we in h steps want to have a control difference which depends on our 5% settling time. Yeah, we have here in the equation what the control difference will do in many steps, decrease by my lambda factor step by step, and now we have a prediction 8 steps into the future of this value, and now this value and this control difference we can put together to get finally an equation for y of k. Let's look. The combination of this equation and the previous equation, of both equations, let's look into my paper. Both equations, C paper, page, what is this? Page 81. Page 81. I open this page 81 and then have a quick look on the equations and try to follow the ideas of these equations. Here you see what I have done just before. The model output h steps in the future calculated by the actual model situation and using the y of k controller output, which is constant for 8 steps. So what I do is now I calculate the difference from future situation minus actual situation. So I subtract from this equation, I subtract xm of k. So I just subtract xm of k, this equation. Okay, I take this equation and subtract 1 xm of k. So xm of k plus h, this minus xm of k. So you see here's an xm of k with minus a1 to the power of h, and with this subtraction I get this one here. So this is a very simple way. So this is a difference between the predicted process output and the actual process output. Okay, the same I can do with the previous equations where I say, okay, I want to also to have the change of the process output. I have to convert this into the control difference expression. Control difference is desired value W minus actual value X. So with this replacement, in this equation, this control difference goes down with the lambda h factor. We can convert the process change from now to future into this equation. So this is a green result, this is a blue result of the second part, green result of the first part of the theory, and now I set this in one equation equal. So that I say the blue part process difference must be the green part process difference. And now look what happens if I do this. I have here the model output. I have here the unknown controller output for one step. Process parameter, prediction horizon, process parameter, desired value, measured process output, and 1 minus lambda, so this user value. So this is now W is given, this is measured, this is calculated by the model, and I can solve this now to y of k. This solution comes here in this equation. So very simple, y of k is the green part plus this divided by this. And you see this is the expression in this equation, and this is modified a little bit by you see here is a 1 minus a1 to the power of h. Here again this is the same expression, so we have here an xm of k divided by a km. So let's look for this final equation. I copy this and we will talk about this equation in the next step. Result of this combination is solution y of k is a coefficient, I call this a sub o, times the actual control difference. W is the desired value, x is the measured value of the process, plus a second coefficient times the model output which I have calculated in this actual moment. So we get a very simple equation, because a sub o and a sub 1 are coefficients which I can calculate before I start controlling. Let's look what is the size of the coefficient a sub o is 1 minus our lambda factor with the 5% tolerance range. Note that is coming from my 5% settling time. Km model process gain, I must know because I have identified my model, and the A1 is also a model parameter, H the horizon. So these are all values which are known, and I can calculate this value, this A sub O, in a previous step. Note that this is a controller output, this is a control difference, and this is a constant factor. So what we see in the first part here, this is nothing else than a P controller. And we have to discuss later in another video what is the change of this. That is a P controller, but now this gives an I part. I will explain in one of the next sub-chapter. Yeah, you can find it, see in chapter 9.12, in addition to explain why this is just the behavior, the PI the PFC controller for a PT1 behaves very similar to a PI controller with a P part and with an I part. And A1 is also given to 1 divided by a process gain. Okay, so I think this is the theory, rather strange. I need some time to really follow the explanations. See docs in the Lernraum. There is a document of Professor Haber at Fachhochschule Köln who explained this in other words, and there is a part of a book from Mr. Richalet, and the link to the Amazon way to buy this book from Mr. Richalet, just a complete book explaining experience with this controller type. Yeah, look into the docs in Lernraum. The demonstration with my simulator comes then with the next video.